Hi everyone, my name is Naina. I'm a final year computer science student and a research intern at Madhvani AI. I'm going to be presenting our work on adaptive COVID-19 forecasting via Bayesian optimization. This work was jointly done by Vadvani AI and members of the COVID-19 Data Science Consortium. So here's the outline for the presentation. I'm first going to discuss the motivation behind epidemiological forecasting and the challenges associated with it. Then we'll take a quick look at existing epidemiological models. I'll discuss the key ideas behind our work, that is, parameter estimation via Bayesian optimization, take a quick look at the experimental results, and end with some concluding remarks. As we all know, the COVID-19 pandemic has had a devastating impact all around the world. To mitigate the effects of the pandemic, it's important to be able to predict the number of infections in the future. Accurate forecasts of infections at a fine spatial granularity can be employed for multiple use cases. This includes containment efforts, that is, identification of containment zones and deployment of law enforcement personnel, medical capacity planning, which includes provisioning for adequate medical resources as well as staff, and scenario analysis for policymaking, which involves decisions around lockdown restrictions, testing policy, and recovery guidance. The goal here is to predict the case counts for various local regions, such as districts or cities, under different scenarios. The plot on the right shows you four case count variables with time, similar to plots shown by most COVID trackers that you may have seen. Blue indicates confirmed cases, green is recovered, yellow is active, and red is diseased. The COVID trackers show you the numbers so far, and the task here is to predict the case counts in the future under various scenarios. A scenario could be specific changes in the lockdown restrictions or testing policy, or it could simply be a continuation of the status quo. There are also multiple aspects to consider. First, we need to build models and generate forecasts that are contextualized for different regions and time periods, because the testing, recovery, and care policies, as well as the conditions on ground, often vary. Looking at the plot on the right, we see how different case counts vary across two different Indian regions, Mumbai indicated by the dashed lines, and Pune indicated by the dotted lines. Until now, we've seen four variables. These are confirmed, recovered, active, and diseased. But in most cases, it might be important to stratify or break up these counts further by severity, age, or subregions such as wards. Finally, the accuracy or fidelity criteria also varies with the end user. For example, in case of medical preparedness, we need forecasts at least for the next month that are accurate in terms of the relative error, whereas for lockdown policy, a directional ordering of scenarios might be more suitable. Before getting to our proposed solution, let's quickly take a look at some of the existing models. As you can imagine, there are a multitude of forecasting models out there. All of these models largely fall into three broad buckets. The first set is the curve fit models, which is just another name for simple machine learning based forecasting models. These are based on learning algorithms that fit to data, but they are often not very interpretable. So there's a big risk of going wrong if the data is bad. The second category of models is compartmental models. Here, the whole population is divided into different compartments based on the stages of the disease, and people move between the compartments at some rates. Examples of such models are SIR and SEIR. The benefit of this family of models is their parsimonious and interpretable nature. They don't have a large number of parameters, but their parameters need to be accurately estimated. The third category is agent based models, which capture behavior at the level of an individual agent. These tend to have a lot of parameters, which makes them non trivial to calibrate with real data. Given the practical requirements, the data constraints, and the modeling tenets, most of our team's practical forecasting operations have been focused on compartmental models. Additionally, though there do exist parameter estimation methods, those are typically very model specific and limited to specific assumptions on the generated process. In a compartmental model, we map the various stages of disease progression to compartments, and we divide the entire population of a region into these compartments and track the counts as they change with time. For instance, consider the model shown here. This is one possible example. Here, S corresponds to the susceptible compartment, E is exposed, I corresponds to infectious, the next two compartments correspond to the post infectious stages, and R and D are the recovered and disease stages, respectively. This model comes with transition dynamics that govern how the compartmental counts change over time. Skipping over the details, the main thing to remember here is that there are a few important parameters. For example, infectivity rate, which is essentially how many people an infectious person could infect in a day. The others are the probability of death versus recovery and the average durations of the compartments. The big challenge is that these parameters vary across time, regions, and population groups. There is also a dependency on lockdown and testing policy. So we have no choice but to estimate these from actual observations using machine learning techniques. The key idea in our approach is to estimate parameters in a model agnostic way via Bayesian optimization. As with any supervised learning, there are two phases: training and prediction. In the training phase, the goal is to find good parameters for a specific model family using the observed data. The model family is usually described by a parametric form, say f theta here. The SEI HRD model in the previous slide is an example of such a family with theta representing all the parameters. The goodness of a model is quantified by specifying a loss function L suitable for the application scenario. For example, in case of medical preparedness, we might wish to optimize for mean absolute percentage error or MAPE on a 4-week horizon. The actual optimization process is essentially a search for the best parameters theta. In order to do this in a model and loss function agnostic fashion, we use sequential model optimization techniques such as the tree structured Parson estimator. It's fairly straightforward to employ other Bayesian optimization techniques as well. Though the Bayes-opt approach provides good parameter fits, a key drawback is that it provides point estimates with high variance. Most epidemiological forecasting applications, however, need robust estimates as well as confidence intervals. The posterior distribution P of theta given D is constructed based on the observed loss values on the data D. When the losses correspond to the negative log likelihood of the exponential family distribution, then the posterior distribution P of theta given D is given by this equation here on the slide. Here the constraint C is estimated via validation on a small future holdout set. Given multiple representative trials, we can employ this idea to construct a posterior distribution on the parameter space, essentially a weighted ensemble of models. Given an ensemble of these models, we associate each model theta I with a weight wi. We can then obtain robust estimates by considering the mean forecast. This is essentially Bayesian model averaging. To generate the forecast distribution profile for any future time t, the forecasts from all models are sorted. Then the probability distribution function, which is essentially wi, is used to generate the cumulative distribution function and thereby the desired quantiles and confidence intervals as well. We evaluated the efficacy and flexibility of our approach applied to the Seer family of models on COVID-19 case data of multiple Indian districts for different periods, as well as synthetic data relative to other baselines with relevant choices of loss function and varying data reliability. This slide shows the result with the SEI HRD model for 4 regions with train and test periods chosen from July. The forecast variants shown correspond to the best fit, the average of the 10 best trials, and the weighted ensemble of all trials. The loss function here is the average MAPE on all the key case counts, that is, confirmed, diseased, recovered, and active. The ensemble mean provides a stable forecast with a test MAPE of less than 10%. Our approach is also found to perform well on US regions relative to other models that are part of the RICLAB COVID-19 Forecast Hub. To conclude, we consider the problem of epidemiological forecasting, which is an important problem with far-reaching implications, especially due to the ongoing pandemic. We propose 2 key ideas. The first is parameter estimation using Bayesian optimization, and the second is the uncertainty profile generation from the model ensemble. The proposed approach is agnostic to the choice of model family and loss function and enables accurate forecast for fine-grained spatial regions. We obtained promising empirical results on Indian cities and US states. This approach is currently being used for medical capacity planning for some impacted Indian cities and states. We are working on model extensions to incorporate testing volume and stratification and plan to open source our modeling codebase in the future. Thank you.